So, if you look at section 4.3, talking about a right triangle. Here we go. So, two perspectives or ways to think about trig. The unit circle is one way, and the unit circle consists of all those ordered pairs. The other way is to draw yourself a right triangle, and that works the same way. And I would draw the right triangle for the angles 30, 60, 90, 45, 45, 90, and then I could find the ordered pairs that way as well. Or I could find sine, cosine, and tangent from using the triangle. So here we have a triangle. This is literally a review from the pre-trig, except we have the three reciprocal functions. So for this triangle, I'm just going to label them as like opposite, adjacent, and hypotenuse as a little refresher. So instead of saying the sign is y, because we're no longer on the unit circle, the sign would be what two sides of the triangle drew. So sign is what two sides of the opposite and hypotenuse. So Drew, if we were finding then the cosecant, its reciprocal, what would we do? Yeah, remember reciprocal? Flip to find the recip. So it's the hypotenuse over the opposite. Or if I already know sine, I'm probably just going to flip it to get the cosecant. So Scott, cosine would be? Right. And then the secant is? Hypotenuse over adjacent, or I would just take the reciprocal of the cosine. And in KC tangent?
Oh, I'm sorry. Opposite over adjacent.
Opposite over adjacent. And the cotangent is? Adjacent over the opposite. So the pre-trig worksheet that we started with, which is I think 2 weeks ago, it feels like it was a while ago. We started by trig defining sine, cosine, and tangent with SOHCAHTOA. So now we have the cosecant, the secant, and cotangent defined using SOHCAHTOA as well, or the reciprocal of the three. The first little diagram is blank, and it says, given the triangle, find the 6 trig functions. So some of your homework tonight will either give you one trig function, and you'll have to label the triangle based off of like opposite and hypotenuse for sine, or it'll already have the triangle partially labeled for you. So we'll just partially label this triangle, like a 4 here. So if you have one side is 2 and the other side is 4, how do I get the hypotenuse? Julian.
You square both of them and add them and find the square root of that sum.
Yeah, what's that called?
The Pythagorean.
Yeah, the Pythagorean theorem. So Pythagorean theorem, if you know two sides of the triangle, you square both of them, add them together, and then take the square root for the other side. So 2 squared, 4 squared equals c squared. So a squared plus b squared equals c squared. So Julian, 2 squared plus 4 squared is?
20.
So if you rationalize, or I should say simplify the square root of 20, what does that become?
2 times the square root of 5.
Yeah, 2 square roots of 5. So a couple of the problems will have the diagram drawn. Use the Pythagorean theorem to get that other side. If it can be simplified, make sure you do that part. So no longer are we on the unit circle, because this could be any triangle. So now you're just using SOHCAHTOA and what we have labeled above. See if you can find the sine, cosine, and tangent. So Ashley, the sine would be?
4 over 2 times the square root of 5.
All right, and what would you have to do to simplify that? Multiply by the square root of 5, and then what else could we do, Ashley, besides multiplying by the square root of 5 with the 4 and the 2?
Simplify those. 2.
Right. So 4 divided by 2 is going to become 2. So I would have 2 square root of 5 and then over 5. So that would be simplified. So this is not on the unit circle because we're just dealing with a right triangle. So looking at the cosine, Asher, cosine would be,
1 over square root of 5.
yeah, so 2 square root of 5. So he said that becomes 1. And then if you rationalize that, it is,
Square root of 5 over 5.
right, so multiply top and bottom by the square root of 5, we get the square root of 5 over 5. And Mackenzie, tangent's just,
4 over 2, which is 2.
yeah, that one's easy. Don't have to worry about that radical over the hypotenuse. So when you go to do the cosecant, I would not use the simplified answer, but instead go back to the original problem, or think that cosecant is the hypotenuse over the opposite. So either go back to the unsimplified form and reciprocal that, or it's the hypotenuse over the opposite. So 2 square root of 5 over 4. What's that become, Julia?
Now the square roots of 5 over 2.
Yeah, nice. So don't use the simplified one because it's more work to try and get that to like flip, and then you still have to take the reciprocal, or you still have to do the rationalizing. So just go back to the original. So secant is a hypotenuse over adjacent. So the hypotenuse again, 2 square roots of 5, adjacent 2. So that should just be the square root of 5 since the 2's cancel. And then Brandon, the cotangent is 1/2. Yeah, 1/2. 2/4, 1/2. Questions? So the two triangles at the bottom of the page, this is a little review of the actual special right triangles that we've been working with. This one has the sine of 45, cosine 45, tangent 45. So I know I'm going to label these with 45 degrees. We're not using the unit circle, but instead, how could I label the length of each side with a little pattern or formula that went with a 45, 45, 90 triangle? Ashley?
The two sides that aren't the hypotenuse are just A.
Yep.
And then the hypotenuse is 8 times the square root.
Right. So if I want to find the sine of a 45-degree angle, it doesn't matter which 45-degree angle you use because they're both the same. So the sine of 45 degrees, and you may already have this memorized from the unit circle, but this is just giving you another way to think about it. So using SOHCAHTOA, the sine is the opposite, which is A, hypotenuse, which is A over the square root of 2. So Scott, what happens with those A's?
Cancel out.
And then that simplifies to Yeah. square root of 2 over 2. So I can find the sine of 45 degrees, or the sine of pi over 4, using the ordered pair because I know the ordered pair, or using a triangle because you know the lengths, the two sides are the same, and the hypotenuse is a square root of 2. The actual length of the side doesn't matter because that side length is canceling once I take the opposite of the hypotenuse. So one, like they could be 10, they could be 20, they could be 50. It's still going to be the square root of 2 over 2. So the cosine of 45 degrees, same thing. Adjacent is A, hypotenuse is A square root of 2. And when you simplify that, you still get the square root of 2 over 2. And that's the ordered pair on the unit circle, x and y. And then Scott, the tangent is just, right, A over A, which is 1. Or the square root of 2 over 2 divided by the square root of 2 over 2 is still 1. So 2 different ways to think about it. You get to pick your way you like to think about it. I'm giving you an option. Well, not me, really. The person that created Trig, those Greeks. So in the next problem, this is my fault. The triangle down below doesn't really look like one side is bigger than the other. So label one with a 30-degree angle, label the other with a 60. When I used the little shape tool, I should have pulled it further one way. So the key thing when you're picking the angles is that angle A has to be across from side A has to be across from 30 degrees. So you can put 30 degrees wherever you want, but the a needs to be across from it. The hypotenuse is 2a, and then the part across from the 60, that's where the square root of 3 should go in. So find the values of cosine 60, sine 30. Cosine 30, sine 60. And if you have these memorized, fantastic. If not, you have a little diagram to use. Drew the cosine of 60 adjacent over hypotenuse. That would be
Square root of 3 over 2. Wait, I did it backwards.
no, that's
I
right.
didn't know.
So so cosine adjacent over hypotenuse.
Wait for 60?
60. Yep.
A over 2a.
So
So it's 1 1/2.
that's 1/2. So then, Drew, if you go to looking at the sine of 30, what's the sine of 30 degrees?
A over 2.
Which is also
1
1/2. Asher, the cosine of 30 is,
Square root of 3 over 2.
and then the sine of 60 is,
Square root of 3 over 2.
what's special about those two angles, 30 degrees and 60 degrees? Asher?
They add up to 90.
They add up to 90. So those angles are complementary angles. And when I have the cosine and the sine of complementary angles, their values are the same. So looking at these two values both times, the angles are complementary for sine and cosine, so their values are the same. Questions? So at the top of the next page, it says because angles 30, 45, and 60, pi over 6, pi over 4, pi over 3, occur so frequently, you can learn to construct triangles for them, which is what we have over here. We have two triangles drawn. Or you can remember the three ordered pairs that are attached to them. So it's kind of up to you how you want to think about them. But those three ordered pairs are really the same values on the triangles. So whether you create a triangle, like the two we have on the previous page, or you think of the three ordered pairs on the unit circle, you're going to get the same values. Anybody know the three ordered pairs? Ashley, do you know them?
Square root of 3 over 2 and 1/2. Square root of 2 over 2 and square root of 2 over 2. And 1/2 and the square root of 3.
Nice job. So that would be starting on the unit circle. My first angle, pi over 6, pi over 4, pi over 3. Those would be those three angles. So see if you can find the sine of 30, which is really pi over 6, sine of 45, sine of 60. See if you can calculate those 9 values. And if you have them memorized, fantastic. You can draw the triangle, you can write the ordered pairs. Get them memorized. 31, 22, 13, right, Drew? All divided by 2.
Yeah.
Drew, that was pretty quick. Yeah.
On the ball for a second.
All right, Drew. Sine 30, 45, 60. What do you have?
Square root of 3 over 2. Square root of 2 over 2. 1/2. Is it wrong?
Yeah.
Wait, what is it?
1/2 square root of 2 over 2.
I keep doing it backwards.
You got to start with 31.
Yeah.
Yeah.
All right.
And cosine, comma sine. Do you cosine, comma sine?
Yeah.
So So 1/2
1/2
square root of 2 over 2
Square root of 3 over 2.
square root of 3 over 2. There we go.
Oh my gosh.
So then what you gave me for sine, cosine would be the square root of 3 over 2, square root of 2 over 2, and then 1/2. Julia, how about tangent? Yep. Good. So tangent is really 1/2 divided by the square root of 3 over 2. Our half, the two parts cancel, and we have 1 over the square root of 3, which is square root of 3 over 3. The tangent would be sine cosine y over x, that's just 1. And then as she said, the tangent of 60 degrees is the square root of 3. Because my half, the denominators cancel, and you end up with the square root of 3. Questions? So underneath, and we just talked about this in the previous page, but I don't have it underneath. I think underneath it says, what do you notice about the sine of 30 and the cosine of 60, and the sine of 60 and the cosine of 30, which we kind of already talked about on the previous page. So, what do you notice about those two? They're the same. Oh, I don't even know where mine went. My little thing disappeared. But they are the same. So, underneath, it talks about a term called a co-function, specifically of complementary angles, angles that are 90 degrees or pi over 2. So when I have a sine, its co-function is cosine. Sine and cosine are co-functions. Tangent and cotangent are co-functions. The secant and the cosecant are co-functions. So what that means is that those values, those functions, have the same value if they are complementary angles. So if I have the sine of 20 degrees and the cosine of 70 degrees, those two values would be the same. We could plug it in the calculator and see that they have the same values. So the co part, cosine, sine, cotangent, tangent, cosecant, secant, it's because they're co-functions. So different from reciprocal. So these are co-functions if they're complementary angles. The bottom two questions, we're not actually going to calculate, but we're going to check them just to make sure that it does work. So it says find using co-functions and complementary angles. If I had the sine of 62 degrees, essentially we want to know what is its co-function. So sine goes with cosine, and then the cosine of what angle would be the same as the sine of 62 degrees? Julian? 28. Because 62 and 28, both of those angles are complementary. They make a 90-degree angle. Scott, you have your calculator on your desk. Just make sure it's in degrees. Just checking to see, like, does this really work? Is it true? If you can put in the sine of 62 and then the cosine of 28. And what are the answers? And those are definitely equal. So it is true, they are co-functions when you have complementary angles. So sine and cosine, tangent and cotangent, secant and cosecant. So then letter B says the tangent of pi over 2, pi over 12. So tangent and cotangent are co-functions. How would I find out the angle that goes along with that? Julian?
You would subtract pi over 12 from pi over 2.
Yeah. So if they have to be complementary, it's two angles, positive angles, that add to be pi over 2. So that means that I have to take the angle that I have and subtract it from pi over 2. So I'd get a denominator of a 12. That means I have 6 pi over 12 minus pi over 12, Julian, which is
5 pi over 12.
5 pi over 12. So they are co-functions as well. So it's a property that isn't semi-useful, but every once in a while we'll see it and it'll help benefit us to help solve the problem. So we're going to do one other thing, and it's more of just kind of defining a couple of things, and it's at the top of your next page. And then I'm going to let you you start the one part of the homework in class so that you have kind of that taken care of. But if you just flip to the top of the next page of notes, at the top of the next page, there's something called fundamental trig identities. An identity is a basic property. So if you think of properties of, let's say, squares, squares have 4 congruent sides, they have 4 right angles, they have 2 pairs of parallel sides. Those are all properties, or technically identities of squares. A lot of things have properties, a lot of things have identities. So the first 6 that you see here are called reciprocal identities. Some of these are in that trig facts packet. So if I have this sign, what do you think would be the function that's the reciprocal of the sign? And we've talked about this. So what's the reciprocal function of the sign? Or what's its buddy function? The cosecant. So the reciprocal identity says sine is equal to 1 over the cosecant. So that is how a reciprocal identity works. So if I have the sine, or if I have the cosecant, I could take 1 divided by the cosecant and I can find the solution for sine. We did the one underneath it when we were using the calculator and plugging in angles on Wednesday. So if I want to know what the cosecant is, I can take 1 divided by the sine to figure out the cosecant, because that's the only way you can find cosecant in the calculator. And that's called a reciprocal identity. So reciprocal is taking 1 over the reciprocal function, that reciprocal part 1 over. So cosine, Julia, would be 1 over the secant, or the secant is 1 over the cosine. And again, that goes along with those calculator problems that we did, because the only way we can find cosecant, secant, and cotangent in the calculator are using the reciprocal functions. And then the tangent would be 1 over the cotangent, or the cotangent is 1 over the tangent. So reciprocal functions, 1 over something. The next 2 are the quotient identities. And the tangent one was the second to last term on the front of the trig packet. So it's different from a reciprocal, because reciprocal is 1 over something. A quotient is literally 1 function divided by another function. So what 2 functions make the tangent? Julia? Sine and cosine. So sine over cosine, or y over x on the unit circle, really sine over cosine, is how you find tangent. So if I know y and x, I can find tangent, which is really sine and cosine. What do you think for the cotangent? Asher?
Secant over cosecant.
You would think so, yes. True?
Cosine over sine.
It's cosine over sine. Asher, which is actually still kind of like the secant over the cosecant, but we try and use the 3 basic functions to decide or define things, so the 3 original functions. So cosine over sine. The last term on here is the Pythagorean identities, which very similar to Pythagorean theorem. There are 3 of them. So the first one deals with sine and cosine, and it says sine squared plus cosine squared equals 1. And this identity is because the cosine is x and the sine is y. And if I'm using the Pythagorean theorem, a squared plus b squared is supposed to equal c squared. This 1 is my hypotenuse of the radius. So x squared plus y squared equals 1, or sine squared plus cosine squared equals 1. So that goes directly with the Pythagorean theorem of having a triangle, x and y representing my sine and cosine. There is a second one and a really cool proof in your book, if you liked proofs. So there is really cool proof. But the second one says 1 plus the tangent squared equals the secant squared. Ashley, did you have Mr. Warnock? Do you like proofs? No. So if you look in your book, there is a proof to show you how 1 plus the tangent squared equals the secant squared. And then the final identity for the Pythagorean identity, and all of these are from the Pythagorean theorem, a squared plus b squared equals c squared, is 1 plus the cotangent squared equals the cosecant squared. So having them kind of up here will help us. We're going to use them on Monday. So this is why Monday is way more interesting than today, because we're going to be using these theorems and identities. So in your packet, if you will flip to page 27. Page 27 has 3 little word problems, and at the top it should say right triangle trigonometry applications. These 3 problems are part of your homework, and I think you probably can do them now. But you're going to draw yourself a diagram, and then after you have the diagram drawn, you're going to label the sides of the triangle and decide based off the sides that you have, do those sides apply to sine, cosine, or tangent. So looking at number 1, a surveyor is 500 feet from the base of a large tree. And you can get creative and draw a tree, or you can just draw a vertical part of the triangle. Okay. That's my large tree. If I have a surveyor, so that's a guy that literally walks around with a special tool in his hand called a astrolabe and measures things, trigonometry like angles and stuff like that. So that's his job. If he's standing 50 feet from the base of the tree, where is he? Where would 50 feet from the base of the tree be? Casey? Away from the tree. He's still on the ground. Away from the tree. So here's my little guy. 50 feet away from the tree. On the ground. The base of the tree is on the ground. It says that this surveyor measures the angle of elevation to the top of the tree to be 71.5 degrees. So I know I have to make a right triangle. So we're going to make a right triangle to go to the top of the tree. And he's measuring that angle from him. He has this tool in his hand, and he's measuring that angle to be 71.5 degrees. How tall is the tree? So what part do we want to find? The opposite part. Label it X if you want. Label it opposite if you want. We want to find the opposite. We want to find the X. So looking at the 2 sides of the triangle that you have, we have opposite and adjacent. Which trig function uses opposite and adjacent? Tangent. So I would want to use the tangent of my angle is equal to the opposite side over the adjacent side. Fill in the numbers that you have. Use your calculator and solve for the height of the tree. So you're going to do the same thing for number 2 and the same thing for number 3. Questions? If you have physics, did you do something like this in physics?
Yeah, sort of.
Yeah.
We did some, yeah.
The other part of the homework is in the book, and you'll have a triangle drawn for you.